Now let's get into some reactions of amines. So the first couple that we're going to see are really review in a lot of ways. We're going to look at electrophilic aromatic substitution and then nucleophilic aromatic substitution. So it turns out that pyridine is deactivated towards EAS, and that deactivation arises from the electron withdrawing effects of nitrogen atom in that ring. So usually the EAS requires unusually harsh react conditions, and Friedel-Crafts alkylations and acylations fail. So keep that in mind for multi-step synthesis. So let's take a look at the observed reaction down here below. So we have pyridine reacting with HNO3 and H2SO4, and where we see this placing the substituent, where the nitro group goes, is at the 3 position or the meta position. So it adds right here. Now we can reason why this occurs by looking at the mechanism down here below. So when we look at the reaction, right, so let's go through this in detail here. So when we look at this reaction, right, we see our nucleophile attacking nitrogen atom here, right? Electrons coming over to our oxygen atom. What that does is that puts a positive charge on our nitrogen right here. So you get a plus charge there, right? And then of course you get the other resonance structures along with that. So this happens when we attack at this 2 position, but it also happens when we attack at the 4 position. Remember from chapter 17 that ortho and para have, other than where things are substituted, they generate the same types of resonance structures, right? So they have the same issues with the positive charges on the corresponding atoms in that ring. Right, now, what we would like to try to do here is we would like to avoid having a plus charge on nitrogen here. Now, it turns out that the plus charge on nitrogen is not necessarily a bad thing, right? But a plus charge with an incomplete octet is a bad situation for nitrogen. It's electronegative and it wants to have, right, it wants to have a full octet here. Now when we attack at the meta position, so here's our 3 position, or the meta position, right, we get a plus charge, right, on our shoulders, so those 2 positions, right, and then 1 over here, right, and I'll let you guys put in your arrows for this. But in the end, what we do is we simply avoid, when we attack at the meta position, we avoid having the positive charge and an incomplete octet on nitrogen. Okay, so there's a couple problems that we have with EAS2 on pyridine. It's deactivated already, right? We have this lone pair on here. Now, when we're in the presence of electrophiles, that electrophile, through a Lewis acid-base reaction, can react with that nitrogen and put a plus charge on nitrogen, and that makes this molecule even more deactivated. So as far as our class goes and homework and stuff like that, we'll just go ahead and substitute at the meta position and not really be concerned with these problems unless it's stated in the question. Now, there are some examples of EAS that do work on pyridine industrially, and these are shown below. Notice high temperature here, right? Still high temperature over there. And also that we're still substituting here at the meta position. All right. Now, the nucleophilic aromatic substitution, the mechanism is different. So pyridine is deactivated towards EAS, but it's activated towards attack by nucleophiles in NAS. So we want a good leaving group at either ortho or para position, and then we can do NAS. Well, let's look at the general reaction down below. So we're going to go through and we're going to play around with the mechanism here a little bit. But let's take a look at the first step. So what I've shown down below are some intermediates here. So what I want to do is I want to show the first step of this reaction, at least for the 2 and the 4 attack. So let's come around here and do this. So with this, it's NaOCH3, so sodium methoxide. Right? So step number 1 of this reaction has methoxide coming around and attacking here, and then coming over and getting an additional lone pair there, right? So we already are starting off with 1, now we're going to have 2. So that's going to lead us down here below to what we see for this C2 addition, right? So that's going to be our intermediate resonance structure for this mechanism. Now, for a nucleophilic aromatic substitution, the nucleophile, now remember for NAS, that nucleophile attacks our ring. And what that does is that leaves this, a negative charge on the ring. So remember, unlike EAS, which leaves a positive on the ring, NAS leaves a negative on the ring. So here, it's better to have that negative charge on nitrogen because nitrogen is greater in electronegativity than carbon. So what we want to do is we want this situation to occur. And that occurs both at the ortho, or the 2 position, and the para, or the 4 position. Right? So at the meta, we simply avoid having that negative charge on the atom that we desire. Right? So NAS works well, EAS not so good.